Halli hallå, as we say in Sweden. I'm Rasmus Båth, and welcome to this last part of a three-part introduction to Bayesian data analysis, which will go into the how of Bayesian data analysis, how to do it efficiently, and how to do it in practice. But I'll warn you, we'll just make the tiniest scratch on the far-reaching surface that is Bayesian computation. The goal is just for you to get some familiarity with words like Markov chain Monte Carlo and parameter space, and to be able to run a simple Bayesian model using a powerful Bayesian computational framework called STAN. Also, if you haven't watched part 1 and part 2 yet, and especially if you didn't do the exercise in part 1, I really recommend that you do that first, because what's going to follow isn't going to make much sense otherwise. Also, this part 3 is quite a lot longer than the other parts, so feel free to take a break at any time. So, what is the problem with how we have performed Bayesian data analysis so far? Well, we've really coded things from scratch, and from my experience, that is slow and error-prone. And it's especially slow because we've been doing approximate Bayesian computation, which is the most general and conceptually simplest method, but also the slowest method for fitting a Bayesian model. But there are many faster methods for fitting Bayesian models that are faster because they take computational shortcuts. And these faster methods have in common that they require that the likelihood that the generative model will generate any given data can be calculated rather than simulated. So what we did when we did approximate Bayesian computation was that we defined a generative model function that took a fixed parameter value and simulated some data. And we figured out the likelihood of the generative model simulating the actual data by running it many times and then counting how many times it produced data matching the actual data. And all this simulation can be very time consuming. And faster methods require a function like this that takes both data and fixed parameters as input and directly calculates the likelihood of these parameters producing the data. It's not always straightforward to calculate the likelihood for any generative model, but for a large number of generative models, someone has already done this work for you. For example, for most common probability distributions, the likelihood is easy to calculate. Another thing faster methods have in common is that they explore the parameter space in a smarter way. Rather than just sampling from the prior, as we have done, faster methods try to find and explore the regions in parameter space that have higher probability, using different, more or less smart methods. More about parameter spaces soon. But finally, it is important to remember that what you get from using a faster computational method are samples as if you would have done the analysis using the type of approximate Bayesian computation we did in part 1 and part 2. You just get the result much faster. So if you're using a potentially faster method that you don't completely understand, but you do believe it does its job, then you could interpret the result as coming from the simple approximate Bayesian computation procedure we used in part 1 and part 2. It's a little bit like when you do optimization. The simplest but slowest method is to do an exhaustive search of all possible parameter combinations and return the optimal combination. But this would just often take forever. So if you then use a faster method like Nelder-Mead optimization, you could interpret the resulting optimum as being the result of an exhaustive search, which is easier to understand maybe, if you believe the Nelder-Mead optimization worked, that is. Now, this slide mentions the concept of parameter spaces, and since we haven't mentioned that before, I thought we would take a little detour and look at the parameter space of a slightly more advanced Bayesian model. So these slides are borrowed from another presentation I held at the 2016 European R users meeting in Poland, so you will have to excuse the sudden change in graphical style. So here is the most advanced model we've looked at so far, but here shown as a nice little model diagram. The data were 2 counts of successes, x1 and x2, out of n1 and n2 trials. We modeled this data as being generated by a binomial distribution. In part 1, I think we called it a generative model of people signing up for fish. but that generative model is more often called a binomial distribution. The squiggly little tilde attached to the arrows should here be read as is generated by or comes from. We have two parameters, which means we have a two-dimensional parameter space. But it's a pretty uninteresting parameter space, as the parameters are not really related in any way. You can easily see that in the diagram. P1 relates to x1 and P2 only relates to x2, but the streams never cross. Let's have a look at another simple Bayesian model, but with a more interesting parameter space. So say you have some outcome y and you would want to model how that depends on another variable x. Then a simple approach is to model this relationship as a line and use linear regression. But which line should you choose? One common approach is to calculate the difference between the line and the outcome variable and try to find the line that minimizes this difference. So maybe this line is better, maybe not. Actually, if you try all different lines, you'll find that this is the line that minimizes the difference. However, this is not how you look at linear regression from the perspective of statistical modeling. In statistical modeling, you instead use probability to posit a generative model, a little story for how the data came to be, and the generative model behind classical linear regression goes like this. So, we have some outcome y, and here we read from the bottom of the diagram or from the top of the text representation to the left, whatever suits you. So, we have some outcome y that comes from normal distributions that all share the same standard deviation sigma, but that have different means mu. And here the mu depends on the predictor variable x through the equation for the line. So for each y, you take the corresponding x and multiply it by the slope parameter and add the intercept parameter, and that gets you the mu for that y. Now, this model has three parameters, three unknowns: the standard deviation sigma, the slope, and the intercept. And these are what we want to figure out. But to the right, I've just visualized this model for some fixed parameter values so that we can take a look at an instance of this model. So the black line shows how the mean of y changes as a function of x, and the shaded lines show a band of normal distribution seen from above. The stronger the shade, the more likely it is that a data point will fall in that region. Now, this is a generative model, but it's not yet a Bayesian model. For that, we need to represent all uncertainty by probability and add prior probability distributions over all parameters. Since smart priors are not really the focus here, we're just going to add dumb, flat, uniform distributions for the time being. Okay, we have a Bayesian model. Let's add the data we looked at before to this. Here I added the data points to the fixed instance of this model. The bluer a data point is, the more likely it is to be generated under this specific instance of the model. So you can say this plot on the right shows the likelihood of the data in data space, which has the dimensions x and y. But we can also look at the likelihood in parameter space. Holding the standard deviation sigma constant for now, we have two free parameters, the intercept and the slope. And the point on the left shows where we currently are in parameter space, at an intercept of minus 0.5 and a slope of 0.9. And the color of this point corresponds to the product of all the likelihoods of all the data points to the right. So now we can move around in parameter space and see how this likelihood changes. If we make the slope steeper, it makes some data points very unlikely, and we see that the overall likelihood to the left goes down. We could make the slope, say, 0, but then other data points become unlikely, and this doesn't get better, even if we change the intercept. This is a pretty good fit, perhaps a bit too steep. A negative slope results in a horrible fit, which makes many data points extremely unlikely. And actually, the parameter combination we started with is the combination that makes the data the most likely, the so-called maximum likelihood estimate. So if you recognize this term, it's because maximum likelihood estimation is a really common way of fitting models in classical statistics. And it does make sense that the parameter values that makes the data the most likely might be a good guess for what the best parameter values might be. But in Bayesian statistics, we're not just interested in one best guess. We're interested in exploring the full parameter space and in how probable different parameter combinations are. And we're almost there. Instead of searching through parameter space for a best parameter combination, we could evaluate the likelihood of all parameter combinations, or at least a fine grid of combinations. So here we have the likelihood of the data given different combinations of intercepts and slopes, which can be written more compactly like this. That is, the likelihood of the data D given a parameter combination theta. But as we said before in this tutorial, we're not really interested in the probability of the data. We know what the data is. What we want to know is the probability of different parameter combinations given the data. And what we've realized before is that the probability of a parameter combination is proportional to how likely it is that that parameter combination generated the data, weighted by how probable that parameter combination was to begin with. To make this proportionality into an equality, we just normalize by the weighted likelihood for all other parameter combinations, and that gives us the probability of different parameters given the data. And again, this little formula here, of course, is Bayes' theorem. And we can use Bayes' theorem to calculate the probability of all combinations in parameter space. Looking at this posterior probability distribution to the left, we see that almost all the probability is concentrated on a slope between 0 and 1.5 and an intercept between -2 and 1. We could arrive at this probability distribution without having to sample from a generative model. As we for this model could calculate the likelihood directly, it was enough to just explore parameter space and apply Bayes' theorem. Now that we have a posterior probability distribution in parameter space, we can do a lot of useful stuff with it. For example, we could draw a sample of intercept-slope combinations from this probability distribution and then plot the resulting lines back into data space. This now becomes a visual representation of the uncertainty regarding the best regression line. Or instead of looking at this 2D distribution to the left, we could look at the marginal distributions for each parameter. So here again we get that the slope is likely between 0 and 1.5 and the intercept is somewhere around -2 to 1. Alright, that was an example of a parameter space of a slightly more complex Bayesian model and how we could fit this model to the data by evaluating the likelihood for all parameter combinations, or at least a fine grid of combinations. But this is not always so easy, as covering the parameter space can be hard. For example, the parameter space can be vast and multidimensional, and we will not be able to explore all relevant parts of it. The parameter space we just looked at was deceptively simple, as it just had 2 free parameters, but it's not difficult to come up with models that have 10, hundreds or even thousands of parameters, making it impossible to cover all relevant parts of the parameter space using a grid. And we might not even know which part we should explore and where to start exploring. But fortunately, there is a lot of research going into making Bayesian computation easier for you. And many more modern and efficient ways of fitting Bayesian models belong to a class of algorithms called Markov chain Monte Carlo algorithms. So this is a class of algorithms that samples from probability distributions by walking around in the parameter space in clever ways. And it's fair to say that the development of efficient Markov chain Monte Carlo algorithms is a main reason why Bayes became popular again. So, the probability distributions we are interested in Bayesian data analysis are posterior distributions, the probability of different parameter combinations after we have used the data. We mostly care about the parameter combinations that at least have some probability. But the problem with evaluating all possible parameter combinations, or at least a fine grid of combinations, is that you have to decide at what points to evaluate the likelihood before you actually know how the likelihood looks. It's a bit of a catch-22 situation. A Markov chain Monte Carlo algorithm instead explores or walks around the parameter space in such a way that in the long run it will revisit each parameter combination proportional to how probable it is. How it actually achieves this differs between algorithms, but when the algorithm works, and there are many situations where it won't, but when it does, it allows you to start the algorithm in some part of parameter space, record its location as it walks around, and the resulting distribution of visited parameter combinations will be a good representation of the posterior distribution. So here is an example of a Markov chain Monte Carlo algorithm let loose in our parameter space. The red dot is the current location and the black dots record where it's been. And the longer it runs, the better the cloud of black dots represents the posterior distribution we looked at before, where the slope was likely between 0 and 1 and the intercept was likely between -2 and 1. And again, the result would be the same independent of which algorithm we use to fit the Bayesian model, approximate Bayesian computation, evaluating a grid of parameter combinations, or Markov chain Monte Carlo. In theory, at least. Because even if you use different algorithms to fit the model, it's still the same model, right? But in practice, different algorithms can make a huge difference, where some are much more efficient than others. And even if you just look at Markov chain Monte Carlo algorithms, there are a bewildering amount of different ones. You have Metropolis Hastings and Gibbs sampling, two of the most common Markov chain Monte Carlo algorithms, but there are many more with exotic names like Hit and Run, the T-Walk, Particle Monte Carlo, etc. Another algorithm is Hamiltonian Monte Carlo, which can be an efficient Markov chain Monte Carlo algorithm that scales well, but that could be difficult to set up. That is, unless you use Stan. So, Stan is a domain-specific probabilistic programming language influenced by R, C++, and bugs, where bugs does not refer to errors in computer programs, but the bugs language, which was the first widespread programming language for Bayesian modeling, and also the winner for hardest to Google for language. I mean, just imagine when you had a bug in bugs and wanted to Google that. Well, so anyway, Stan is its own language, but it's really designed to be used together with another language, and it has interfaces to languages like R, Python, MATLAB, etc. So what Stan allows you to do is to just define your model, and then Stan takes care of fitting it efficiently by compiling it down to C++ and using Hamiltonian Monte Carlo to fit the model. And if you want to do more serious Bayesian data analysis, Stan is a good place to start. So I said that Stan is a domain-specific language, which means it can't do everything, but it's really good within its domain. And Stan is really tailor-made for defining generative model. So let's take a look at some Stan code. Omitting declarations, here is a minimal Stan program that implements a simple binomial model, basically the same model as in the fish subscription example from part 1. So each Stan program consists of a number of code blocks, where the model block describes the generative model. And here we are stating that some X number of successes out of n trials are distributed as a binomial distribution, where the rate of success P is distributed as a uniform between 0 and 1. This program is going to give you the same as the following R code, where we first draw uniformly between 0 and 1, put that value into P, and then draws X successes out of n trials with this P as the rate of success. So running the Stan program or the R program for a large number of iterations is going to give you the same, a large sample of randomly drawn P's. That is, if there is no data. That is, n and x are set to 0 in the Stan program. No trials, no successes. So here is a plot of a large sample of P's drawn using the Stan program, and it does look pretty uniform, which is the output we also would expect from the R code. However, if we add some data to the stan program and x is set to say 10 with n being say 30, that is we have 10 successes out of 30 trials, then the stan program will produce samples of p that are similar to running the R code with an extra approximate Bayesian filtering step at the end. That is, sampling p's uniformly between 0 and 1 and then filtering away all those p's that didn't result in x becoming 10. That is, stan will generate draws from the posterior distribution of p given the model and the data, x equals 10. The result which you can see in the histogram. A difference here is, of course, that running the stan program is going to be much more efficient than running the approximate Bayesian computation routine in R. Now, it's very important to understand that stan is not actually doing the same as the R code. It does give similar output, but it does not run an approximate Bayesian computation routine. Internally, it doesn't first sample p from a uniform distribution. Stan uses a Markov-Chain Monte Carlo algorithm that walks around the parameter space, here just the one-dimensional parameter space of p, where, if everything worked, the records of this walk will be distributed as the posterior distribution. How stan actually works is out of the scope of this tutorial, but the sweet thing with stan is that it often works. For many models, it's actually enough just to define the generative model, and stan will do the rest. So, more generally, how do you define a model in stan? Well, for that you need to know the syntax of stan. So what I'm going to do now is that I'll breeze through a cheat sheet of the syntax of stan. It will be very brief, but don't worry, in the end you'll get the link to the cheat sheet, so no need to take notes. Alright, a crash course to the syntax of stan. The basic syntax is similar to all curly bracket languages such as C and JavaScript, but vectorization is similar to R. Comments can be written with double slashes like in C++ or a hash sign like in many other languages. So if you look through these statements, you'll see that it looks like something you could see in, say, R. As in C and C++, you need to end each statement with a semicolon. As opposed to JavaScript, R, and Python, stan is statically typed. So the types of all variables, parameters, and data has to be declared in advance. So you have the types you get in all languages, like real numbers and integers. But there are also a lot of types useful in statistical modeling, like vectors and matrices. So vectors and matrices can only contain real numbers. So if you want collections of other types, you would have to use the more flexible array type. All types can have added constraints, and constraints are required for variables acting as parameters. For example, if we have a proportion parameter p, we wouldn't want that to ever be outside the range of 0 to 1. And constraints are how we tell stan things like this. So if you give a parameter no constraints, that's the same as saying it could be anything from -infinity to +infinity. A standard deviation parameter sigma, we might want to give a lower bound at 0, and so on. There are some speciality types with special constraints, like the simplex vector, which constrain all its elements to be positive and to sum to 1. So these were some of the small pieces of a stan program. But looking at the whole stan program, you see that a stan program consists of a number of code blocks, where each block fill a different role. So you have the data block, which can only contain declarations, where you tell stan what data this program accepts as input. You have the parameters block, where you declare what the parameters are. The most important block is the model block, where you define the actual generative model. And sometimes you want to calculate derivative quantities like predictions based on the parameters, and the code for that you would put in the generated quantities block. There are more block types, but these are the most commonly used. So stan was a probabilistic programming language, and what makes it a such is that you can define non-deterministic relations in the language. In stan, that is distribution statements, which define probabilistic relations between parameters and data. So distribution statements are written with a tilde and allow you to define, say, that X is distributed as a normal distribution with mean mu and standard deviation sigma. There are many built-in distributions in Stan, and it's not too difficult to define your own distributions. As in R and MATLAB, many of the functions are vectorized. That is, they work on vectors as well as on reals and integers. This allows you to write more concise code, and you can often avoid writing for loops. Note that, as opposed to R, for loops are not that slow in Stan. To pick out individual values from vectors and matrices, you use square brackets, and if you're used to Python or C++, you need to remember that indexing starts at 1. So, now we have all the pieces to put together a minimal Stan program, here implementing a binomial model. Again, the same model as we used in the Salmon subscription example. So, first we declare what data we have in the data block, an integer n, the number of trials, and an integer x, the number of successes. The model has a one unknown, one parameter, which is the underlying frequency of success p. You can't have less than 0 or more than 100% successes, so we need to constrain p to be between 0 and 1. Finally, we describe the generative model where we state that p is distributed as a uniform distribution between 0 and 1, that is, this is the prior on p, and x is distributed as a binomial distribution with n trials and a p frequency of success. Again, you could read this as that we first sample p from a uniform distribution and then sample x from a binomial distribution. You could do this, but it's not really what Stan is doing under the hood at all. One way of seeing this is to put the uniform distribution statement under the binomial. So the Stan model is going to run just fine, even though from a sampling perspective we're doing stuff in the wrong order. So now we just need to get Stan to compile and fit this model somehow. This is usually done from another language, such as Python or R. And assuming model_string contains the model from the last slide, this is how you would do it. First, you need to define the data, and then you run the stan command, passing in the model string and the data. And after waiting a couple of seconds for Stan to compile and fit the model, you'll get the Stan object back, which contains a large sample of parameter values representing the posterior distribution for p. Okay, so that was a whirlwind tour of Stan. And if you feel confused, that is totally fine. It's not easy to learn a new programming language in 10 minutes. Nevertheless, it's time to now try out Stan in exercise number 2, Bayesian A/B testing using Markov chain, Monte Carlo, and Stan. So the purpose of this exercise is not to become masters in using Stan. The main purpose is just to install Stan and get something running. So step 1 is to install Stan for R or Python, which might not be the easiest. So for that, just follow the first link. Then, with the help of the Stan sheet we just went through, we will try to replicate the analysis we performed in exercise 1 in part 1 of this tutorial. So, just installing a program and redoing something you've done before might not seem like much. But with Stan at your fingertips, ready to do your command, you are able to explore and experiment with Bayesian data analysis much more easier. So this is a really good exercise worth doing. I'll be waiting here when you come back. Alright, welcome back. I hope that exercise went well. If you did the exercise, or if you at least took a look at the solution, you should have come across the following figure at some point. It's called a trace plot, and it shows the parameter draws from the posterior for the underlying rates of success for group A and group B, and also their difference. But instead of being displayed as, say, a histogram, which would be easy to read off, we get them as a line plot where the x-axis is the order the parameter draws were produced in. Why is this, and why would we want to look at such a plot? Well, Stan uses a Markov chain Monte Carlo algorithm, which, if you remember, walks around the parameter space with the promise that in the long run, it will visit each parameter combination proportional often to its posterior probability. That is, how probable that parameter combination is after having used the data. Now, note that I said in the long run. As we just allowed Stan to go on for a little while, we cannot be sure if our run was long enough. And while we can never be 100% certain of this, we should at least do some Markov chain Monte Carlo sanity checks, because there are many things that could go wrong. For example, our initial parameter values might be way off. The Markov chain Monte Carlo algorithm has to start exploring the parameter space from somewhere, and if that somewhere is way off, it might just have wandered around in a low probability region and we stopped it before it really got to the bulk of the probability in parameter space. Or maybe the algorithm got stuck in a part of parameter space, which could happen, for example, if it got stuck in a local maximum. So, to try to avoid these problems, you could add a little burn-in when running the Markov chain Monte Carlo algorithm. That is, you let it run around for a while so that it is more likely that it starts from a good starting position. You can let loose multiple Markov chain Monte Carlo walkers in the parameter space, or chains as they are also called, from different starting points and see that they explore similar parts of the parameter space. And finally, when you plot the samples from the algorithm, you should look for hairy caterpillars, which is what you would see if the Markov chain Monte Carlo algorithm worked well. Doing these three things does not guarantee in any way that the Markov chain Monte Carlo algorithm did work well. It's just the bare minimum of sanity checks you should perform. So what could this look like? Here is a trace plot from a model I found online, which one doesn't really matter. But if we look at the plot of sigma, we see that both the blue and the purple chain starts off a little bit off, but later stabilizes. So to throw away the first 1,000 iterations as burn-in wouldn't be completely off. Otherwise, the two chains mixes okay and does have that hairy caterpillar look. The trace plot for beta looks bad, as it gets stuck for long periods and looks more like a cityscape. A solution in this case could just be to run the model for a really long time, which could make beta look more okay, but as it is now, it looks a little bit off. If we instead look at the output we got from Stan during the exercise, we see that everything looks okay. Big, fat, hairy caterpillars. Again, this is no guarantee everything is alright, it's just the first sanity check. But since this model is so simple, I'm pretty sure it's okay. So, we looked at Stan, but there are many other tools for fitting Bayesian models. Just off the top of my head, for R we have MCMC pack, an old stable package that contains a lot of pre-specified models you can use out of the box for regression modeling, etc. Then there is JAGS, which, like Stan, is a domain-specific language to build Bayesian models, which has been around for a while. And then there was Stan, and if you want to ease into the Stan language, there is the Rethinking package, developed by Richard McElrath, together with this great intro book to Bayes. And that allows you to define Stan models using a much simplified syntax directly from R. In Python, you again have Stan, using the PyStan interface, but there is also PyMC3, which allows you to define Bayesian models directly in Python. Alright, so it's time to wrap up this tutorial, but first let me say that there was a lot we didn't cover. We didn't talk much about priors, and there are many different methods, more or less principled, for coming up with those. We didn't talk much about statistical distributions. We almost only used the binomial distribution, and since statistical distributions really are just small generative models, there are a lot of different distributions used in Bayesian stats, as they are the building blocks you use when you construct a Bayesian model. We touched on decision analysis, but This is really a whole field of research. We didn't talk about model selection, where you have two or more competing Bayesian models that you want to compare, and where some people use so-called Bayes factors for this. I deliberately decided not to talk about philosophy, and I tried to keep the math to a minimum. But if you're into math, then rest assured there are a lot of Bayesian textbooks full of that. So, to summarize this tutorial, Bayesian data analysis is a flexible method to fit any type of statistical model, and maximum likelihood can be seen as a special case of Bayesian model fitting. Why use it? Well, it makes it possible to define highly custom models, where you can include information from many sources, for example, both data and expert knowledge. And Bayesian data analysis quantifies and retains the uncertainty in parameter estimates and predictions, which is super useful, not least if you want to use the results for some type of decision analysis. And how to do it? Well, with Python and R together with some of all the great packages like Stan, PyMC, JAGS, etc. Finally, if you want to look more into Bayesian data analysis, and I hope you do, I would recommend you pick up something as old school as a book. Both Bayesian Methods for Hacker by Cameron Davidson-Pilon and Think Bayes by Alan Downey are good introductions if you are comfortable with Python. They are also available for free, which doesn't hurt. The book I started out with was Doing Bayesian Data Analysis by John Kruschke, which uses both R, JAGS, and Stan. And don't get fooled by the puppies on the cover, it's a seriously great book. Another great book is Statistical Rethinking by Richard McElrath, which is a fantastically clear introduction to Bayes. It has been called a pedagogical masterpiece by me in an Amazon review, but I do stand by it. And finally, if you want something more math heavy, then Machine Learning, a Probabilistic Perspective by Kevin Murphy is an amazing introduction of machine learning from a Bayesian perspective, or perhaps Bayesian from a machine learning perspective, depending on your point of view. And finally, if you want to try out some more advanced Bayesian modeling right now, I have a bonus exercise for you. Bayesian computation with Stan and farmer Jöns. So it's a farm-themed exercise that takes off from the binomial model we used in the last exercise. And by just changing this model a tiny bit in each question, it will take us through most of the basic stats model, all the way to running a full Bayesian linear regression in Stan. So, that was that. Thank you so much for watching this tutorial and for staying with me to the end. I'm Rasmus Båth, and it's been a pleasure being your guide in this introduction to Bayesian data analysis.